Okay, so let's consider the problem of a user who wants to store a massive database, say, for example, to train an AI model, but he doesn't have enough local space to do so. So one thing he can do is use a remote cloud server, such as an AWS server, to interact with and store the data on. So now the user can make read and write requests to the server to update it or read from it, but how can he ensure that his interaction with the server is kept private? So how can he maintain privacy of his data? So for example, consider a concrete example where there's a hospital storing data about its patients on a server. Then one idea to ensure privacy is to encrypt all of this data. So for example, you can encrypt patient 10's information, patient 1000's information, and so this hides their identity and what diagnosis they have. But turns out this alone is not enough because the access pattern to the server can also leak information. So for example, if the hospital accesses patient 1000's data many, many times, a curious server can now say, well, I don't know who this is, I don't know what he has, but patient 1000 is very, very sick. So you want to hide even this type of information. And this is actually very well known that access patterns leak a lot of information, and attacks such as Meltdown capitalize on this fact. So to model this, Goldratt and Ostrowski in 1996 proposed a primitive called oblivious RAM. So basically, an oblivious RAM is a layer between a user and a server. So now the user interacts with this ORAM instead. So it sends a read or write query to this ORAM. This ORAM is then going to transform this into a bunch of new queries, query hat. So this is not exactly going to look like the original query. And it's going to send these query hats to the server. And after talking to the server for a little bit, it's going to determine some response to send back to the user. First property we expect to have is correctness. So from the user's perspective, all the responses that it gets from the ORAM better look like actual responses from a server that's truthful. So we want this response to correspond exactly to the read or write query. The second property we want is obliviousness. So what this means is that the query hats between the ORAM and the server, these transformed query hats, should leak no information about this underlying set of queries. So these query hats could look like shuffling or moving things around, reading a bunch of things, but at the end of the day, we want this query hats to not leak any information about the underlying queries. So going back to our example from before, you have a user who wants to talk to a server. So one thing he can do, or she can do, is basically run an ORAM internally on her laptop. So now all the queries that the server sees is through this ORAM, and so it cannot learn anything from the access pattern to the server. So another very interesting application of this is in contact discovery. So many messaging platforms these days, such as Facebook, WhatsApp, simply store the full social network graph of all of its users. But in fact, many of these apps just have you directly upload your address book to the server. But this is not really great because this leaks a lot of sensitive information that can be used for things like scams, discrimination, blackmail. And so we want to avoid leaking the full social network graph. So the main issue is that if the server stores all of its contacts, all of its users in the clear, the access pattern to retrieve the contacts from this address book leak information about who the user's contacts are. So for example here, based on the access pattern, the server now knows that Alice and Charlie are the user's friends. And by collecting all this information over time, it can basically reconstruct the full social network graph. So what do? Signal is a messaging app that really focuses on maintaining privacy. And their solution here is to use an ORAM for secure contact discovery. So basically, the user sends encrypted contact queries to the server, so the Signal server, and the Signal decrypts it and sends ORAM queries to its server that contains all of the addresses or contacts, and now uses that to retrieve people's contacts. So now the Signal server or any eavesdropper is not able to learn who the contacts are without this secret key. So this is a very cool application of ORAM, and so hopefully I've convinced you that this is very useful to study. So the main efficiency metric we care about in ORAMs is the number of query hats generated to respond to any single query. So we care about the ratio of the blow-up in the communication with the server. So this is called overhead. So basically, the arrow there is pointing to the overhead of the server. So a lot of research has been done on this, and starting with square root n, after a lot of work, a lot of amazing work, we've finally been able to achieve log n overhead by this work called Optorema. And yeah, so it turns out there's a lower bound showing that this log n is in fact optimal. So now, what's my work here? What aren't we already done? So it turns out up till now, the main threat model considered assumes that the server is passive and honest but curious. So it's going to respond to everything honestly, but it's still going to look at this transcript and try to do some detective work on it. But in reality, an adversary can actually do a lot more. So what if we consider an adversary that actually corrupts the whole server and responds incorrectly? So this is the threat model we consider. And turns out, this is very devastating, because now there's no more guarantees after a server sends back an incorrect response. So looking back at our ORM history, basically, the first three constructions can be made maliciously secure with some extra work without blowing up the overhead by too much. But the ones that achieve almost optimal overhead are in fact insecure, and we actually have attacks on them. So now the question is whether this log n overhead is still achievable, or is somehow this log square overhead construction somehow optimal? So this is the main question that we asked in our work. So is there a maliciously secure ORM with O of log n overhead? And turns out yes. So that's what I proved in the work with Nikon Wafa. We construct what we call Macarama, which is a maliciously secure ORM with O of log n overhead. So this is very exciting, because putting it back in this picture, as we said before, this is in fact the best thing you can hope for, so we can get malicious security essentially for free. But in practice, turns out Macarama, our construction, has a very, very, very large constant. So it's not actually efficient in practice, but it's still a very cool theoretical result. So in practice, people still use path ORM, which achieves log squared n overhead. So we looked at this construction, and again, this is used more in practice because it has smaller constant. And in upcoming work, we show that there's actually an easier way to make this maliciously secure. So currently, they use SHA-3 to make this maliciously secure. And in upcoming work, we show that actually you can do this with AES-NI. And this is very exciting because many more CPUs have our hardware acceleration for AES-NI rather than SHA-3. So we also have a new practically efficient maliciously secure ORM construction. Okay, thank you very much.